Welcome back, folks. Today we're talking linear programming. Now, last time we left off, we were looking at systems of inequalities, sort of like this one we have off on to the right here, where we had a couple of lines that were going to have inequalities attached to them, and then we would shade whatever the region is. For example, with this one, we have our first line it looks to be is the 16 to 16. Our second line is this slower line here. And then we're trapped in this first quadrant. We have to be greater than x is 0, so greater than the x-axis and greater than the y-axis. Now we know this system has an infinite number of solutions, because an inequality will have an infinite number of solutions. Could we find one that maximizes, that gives us the largest possible value for p is equal to 10x plus 15? The answer is we could, but we're going to have to test and check points. This is really all that the idea of a linear program is. All linear programming is a way to find a maximum or minimum value of a quantity if we're constraining it, right? We're constraining it here. We're trying to find the maximum for p. So a linear programming is a way to find the maximum or minimum value of a quantity like p. If we're given some constraints, if we're given something to limit it. Now, what was constraining this one? It was the inequalities, and so that's why the inequalities are called the constraints. Constraints. And the graph, the shaded region, is what we call the feasible region. All feasible means is that it's our possible region. It's something that could work. So any of these answers are feasible. They could work. And the quantity we're trying to maximize or minimize is called the objective function. So this is a lot of words, but what we're saying is we have some objective function, something we're trying to maximize or minimize, inside of a feasible region, a region that we have to test. That region is bound by constraints. And all we're trying to do is we're trying to find a maximum or a minimum value. Now, thankfully, we know we need to test and check, but we have a tool that tells us we don't need to test and check an infinite number of points. And that's the vertex principle of linear programming. What the vertex principle says is that if there is a maximum or minimum to an objective function, so if there's a maximum or a minimum, that maximum or minimum has to occur at what we call a vertice, or one of the corners of the region. This means that instead of having to test every point inside of the shaded region, we just need to test the four corners. And that's actually what we're going to do here. First, let's figure out what the corners are. We have one here, so that's going to be the point 0, 0. We have another point up here, that's going to be 0, 8. We have a point down here, which we're going to have to figure out what that is. And we have a point here. That point looks to be 4, 8, 12, comma, 4. Now this last point here, b, is going to be 16, comma, 0. So we have a whole bunch of different points to test out. Let's go ahead and list these all down where we're trying to find the maximum value. We said we had a point at 0, 0. We had a point at 0, 8. We had a point at 16, 0. And we had a point at 12, 4. Now to maximize this, all we're going to do is we're going to substitute the value into p. So we're going to say p is equal to 10 times 0 plus 15 times 0, or it's equal to 0. We'll do it with 0, 8. We'll say p is equal to 10 times 0 plus 15 times 8. Then we throw that into our calculators to figure out what that will equal. We find out that that will give us 120. So that's looking the largest so far. Let's try 16, 0. P is equal to 10 times 16 plus 15 times 0. That's going to give us 160. So that's looking like the largest. And what about this last one at 12, 14? That would be 10 times 12 plus 15 times 4. Let's throw that one into our calculator, see what it is. 10 times 12 plus 15 times 4. That gives us 180. So the maximum value is 180. Let's write this out. The max is 180, and that is at the point 12, comma, 4. Now we can also do this to find a minimum. All we're going to be doing is we're going to be finding the points, and we're going to be putting this in looking for the smallest value. So go ahead and try that. Tell me what the smallest value is and where it will occur. The smallest possible value, well, let's find this out, could occur at 0, 5, could occur at 2, 1, or it could occur at 3, 0. And how do we check? Well, we substitute these values into our objective function, or our cost function. So we're going to say p is equal to 4 times 0 plus 5, or the top point here, c, will be 5. The next one, 2, 1, p is going to be equal to 4 times 2 plus 1, or it's going to be 9. And then for 3, 0, p is going to be equal to 4 times 3 plus 0, so that's going to be 12. What's our minimum going to be? Our smallest value is 5, and it occurs at 0, 5. So the minimum is 0, 5 at, or the minimum is at 0, 5 and is 5. This is the basic idea of linear programming. We have some set of equations, and then we find our feasible region, we find the bound area, and we test the points. So now we're going to have to graph each of these. Let's go ahead and get started with the first one. Y is greater than 1/2 x plus 2. So we're going to start at 2. We're going to go up 1 over 2, up 1 over 2, up 1 over 2. And now because we're dealing with the points where these intersect, it's super important that we get a straight line here. I'm going to go ahead and make sure I do that. And here we go, our first line. Now y is going to be greater than 1/2 x plus 2. Greater than meaning that we're going to be looking at above this line. Let's go ahead and do our next one. Y is less than or equal to minus x plus 8. So we're going to start at plus 8. We're going to go down. Going to keep going down. Looks like we have a vertex there. Let's go ahead and graph that line as well. And here we have our next line. Y is less than or equal to minus x plus 8. This one, less than or equal to, we're going to be going down from here. And we know that x has to be greater than or equal to 2, and y has to be greater than or equal to 1. So let's put those lines in. And here we have our vertical and horizontal lines. Now, if this one's pointing down, that one's pointing up, and we're constricted into this top right corner, our shaded area is going to be this area in here. Now, what are our vertices going to be? We have one, it looks like, right here. So that's going to be at, it looks like x is 1 and y is 2.5. Our next one all the way up here is going to be 1, 7. And then we're going to have a third point out here at 4, 4. And we're going to put these in to our equation. All right, here we have all our lines. We're trapped into this top region over here due to the x and y's blocks us into here, and we're below the steep line and above this positive line. It looks like the area, our feasible region, is in here. Now, what are our vertices going to be? Not going to be these, that's for sure. What are our vertices going to be? Looks like we have one here. That appears to be the point 2, 3. We have one all the way up here. That looks to be at 2, 6. This one's at 2, 6. And our last one out here is going to be 4, 4. What do we do now that we have our points? We substitute them back into this p equation. So p for this first one will be equal to 2 minus 4 times 3, which will be a minus 10. What about for 2, 6? P is going to be equal to 2 times 4 minus 4 times 6. So that'll be 2 minus 24, or minus 22. And for 4, P will be equal to 4 minus 4 times 4, or that'll be 4 minus 16, so that'll be minus 12. Looks like our largest value, even though it's negative, is minus 10. So our maximum is minus 10, and that is at the point 2, 3. No, these are a little hard. Let's have you go ahead and do one for yourselves. This time, here is our system of equations. We're trying to find a minimum. Go ahead and work on that. Now, for this one, I'm going to come back to you with all of the work done on the graph. Here we are, back with those graphs drawn, those lines drawn. For this sloping downwards, it's above it, and we're restricted again to this top right corner by x being greater than or equal to 2 and y being greater than or equal to 0. Meaning our feasible region is everything going out this way. That doesn't change the fact what we're looking for is our vertices, or the points where two lines intersect our corners. We have one, it looks like here, at 2, 3. And we have another one all the way down here at 8, 0. For this one, we're going to substitute these in. So c is going to be equal to 2 plus 3 times 3, or 2 plus 9 is going to give us 11. Whereas for the second one, c is going to be equal to 8 plus 3 times 0, so it will be 8. Meaning that our minimum will be 8. And that will be at the point 8, 0. Now you have a couple of practice problems that look just like these last couple for your homework, so go ahead and get working on those.